Okay, now that we talked about properties, now we're going to talk about the four different types of curves that we can have. So I've got a rose curve, I've got a Limassol curve, I have a spiral curve, and a lemniscate curve. The two ones that have the most information are most interesting, most fun, whatever, are the rose and the lemniscate. So I am going to talk about what those look like, and then I hope to switch screens so I can also show you graphs of them one at a time. So the first one is the rose curve, and rose comes, it either looks like r equals a number times sine n of theta, or it can be the same thing with cosine, r equals a cos n theta. Now recognize that n and a are both constants that we're going to have numbers in those places. A refers to a distance. So A is like your distance away from the pole. It's like when we did those, what do you call it? It's like when we did those sine cosine graphs, and A was like how far away it was from the axis. So it was kind of a distance thing, less of anything else. So N refers to number of petals. So it's a rose, so it's going to make a little flower shape. It's going to have petals. So if N is odd, so if N is 1, 3, 5, etc., then there are N number of petals. If N is even, so if N is 2, 4, etc., there are 2N number of petals. Okay. So what you can do is you can plug and chug, or you can graph it. I think for sake of time, I'm not going to plug and chug. If you're interested in it, I'd love to sit down and talk with you. But because we're distance and because of time, we're just going to look at the calculator. So we're going to do an example where r equals 3 sine 4 theta. Okay, 3 sine 4 theta. My A is my 3, so that means that like my farthest distance away will be 3, and then my N is 4. 4 refers to N. We just talked about number of petals with N, so from knowing nothing else, N this time is even, so that means that there's 2N, or 2 times 4 petals. It means that I've got 8 petals going to be on this picture. And then my distance, my farthest distance is 3. So those are what those A and N numbers mean here. Okay, I'm going to now share my calculator, I think. So I hope that it's still showing you this. I now have my calculator out. And so for my calculator, you need to make sure that you are in mode of polar. And then we will just double check with this one. I was doing all of them before this in degrees, but I wonder if now I'm allowed to do it in radians. One of them later on definitely needs radians, so I don't know if this will be different in radians or degrees. Okay, so I'm gonna go to my y equals, and I have this all set up just so that it's easy. So we're gonna do the first equation. So if you need to pause to make sure that you have this written in your calculator, 3 sine 4 theta, go for it. Okay, for those of you who are not, we're gonna go and we're just gonna do a zoom standard and see what happens, or a zoom square, it doesn't really matter. Oh, that worked out nicely. Let's actually zoom in a little bit more. Let's check out our window. Because I'm in radians, it goes from 0 to 2 pi. My step is just what the standard was set at, and then my x min and my x max were fine. Let's maybe, if we go to zoom square, maybe we'll be a little closer to it. Nope, not that much closer. You can play around with your window for sake of your time. I'm not going to do that, but you can pause it and play around with your window. If you see there's 1, 2, 3, 4, 5, 6, 7, 8 petals, which is what we said. And then if we were to go and trace, we could see that the farthest distance away would be r equals 3. Okay. So we're going to go back and do a new share. I'm going to go back to my iPad. Hopefully not too painful. And I'm going to write some properties of this. So I left a lot of space up here for rows, et cetera, et cetera. So now I'm going to go and talk about what my properties of this shape are. These are not going to be something that you have memorized, but they're good to talk about and good to know. And again, you can explore more of this on your own. So my domain here is all real numbers. You can plug any value in for your domain and it will work. My range, your smallest value is your negative distance, and then your biggest value is your positive distance. So in our case, it was that 3. In any other case, it's whatever the coefficient in front of the sine and cosine is. It is continuous. You don't have to pick up your pencil, or the computer didn't have to pick up its like cursor in order to draw that all the way out. For symmetry, there's a couple different cases. So if n is even, then all symmetries are true. X-axis, y-axis, origin. If n is odd and it's cosine, then it's just around the x-axis. If it's sine, if n is still odd and it's sine, then it's just around the y-axis. It is bounded. As you can see, it doesn't go on and on forever. It stays in its little flower shape. And its max R value is A, and I'm going to put absolute values around it because if it was a negative value, it would still be positive A. There are no asymptotes here. And remember that something special is number of petals. I'm just writing this again so you have it in a couple different places. It's n petals if n is odd, and it's 2n if n is even. Okay. Put that away just so you can see all of this. So these are things you can notice from our graph. These are things that you can see from what's going on. All right, now we're going to look at the limaçon. I think it's French for snail, so I don't speak French, so I'm sorry if I'm butchering that pronunciation, but we're going to roll with it. All right, a limaçon comes from the form r equals a plus or minus b sine theta, or you can replace the sine and cosine. Give me 1 second. I don't know why I have these A and B backwards. There's nothing special. It's the same A and B. I'm so sorry. I just had to look that up. It's the same. Okay, so one thing to know, A has to be greater than 0 and B has to be greater than 0. They can't be negative numbers. There can be negatives in between them, but them themselves are all positive numbers. So that's good to know. Now there's 4 different types of limaçons. So limaçon is like a big umbrella, and there's 4 special types of it. So the first one is, it's called a limaçon with an inner loop. And when you see the drawings, and you'll figure out exactly what I'm talking about and why it's called that. So if you take a ratio of A over B, and that is less than 1, then it will be an inner loop limaçon. Okay. The next one's called a cardioid. And it's if your A and B divided together are equal to 1. So you can kind of see which general shape it's going to be even before you graph it. The next one is called a dimpled limaçon, which means it looks like there's a little dimple or a little poke in it. And it's if you do A over B and it's between 1 and 2. So it's like 1.1 or 1.5 or 1.87, blah, blah, blah. And then the last one is called convex. And it's if A over B is greater than or equal to 2. Okay, we're going to look at 2 examples of these. We're going to look at 2 of these. So the first one is r equals 3 minus 3 sine theta. 3 minus 3 sine theta. So before doing anything else, is this an inner loop, a cardioid? Oh, I spelled that one wrong. There's an extra I in here. Or a dimpled or a convex? Well, let's make a little ratio. I've got A, which is 3, over B, which is 3, and that equals 1. So that's got to be the cardioid, okay? So we're about to see what that looks like. And then the second one we're going to look at, I'm just going to tell you before I switch screens to the calculator, is going to be r equals 2 plus 3 cos theta. And now let's guess what that's going to be. If I do my ratio a over b, 2 over 3, well, that's less than 1. So then I'm looking at an inner loop. So I'm looking at the first two examples right now. Okay. So I'm going to switch over to my calculator, I think. Okay, so my calculator, if you go, so this is still my flower, how pretty the rose. Okay, now I'm going over here. I'm turning off the first one so I don't see the rose again. And I'm going to turn on the second one so that I get to see the first limacon, which we guessed 3 minus 3 sine theta. We guessed that was going to be a cardioid. So I'm going to just graph it and see what happens. Oh, nice. Again, I believe we're in radians. So if you are not getting what I'm getting as easily as what I'm getting them, go to radians. And then I think I'm still in like Zoom standard. So it just put it exactly how it wanted to go. If you're having trouble with these though, let me know. This, if you look closely, it's got like a specific point there at the origin, and it kind of makes like a little like rounded heart from there. Okay. So that's what a cardioid looks like. And then now I'm going to go and select the other one. Again, pause this video at any time to really explore, dig deep on your own, or change some numbers and see what happens. I just don't have time for that with you. Now we're going to do 2 plus 3 cosine, and we guessed that was going to be an inner loop. So when I graph that, let's zoom in a little bit because that's kind of cool. Let's do window. We'll say x min is -5 and x max is +5. That will be probably zoomed in enough. Oh, no, that's kind of ugly. Let's do y's too, so it's a square. I might be cutting something off, but I want to really look at what that inner loop looks like. Oh, yep, that's nice. See how it has an inner circle inside? It goes inside of itself and then comes back out. So that's what the inner loop looks like. All right, again, explore on your own. I'm going to go back to the iPad and look at the last two, and then we'll do those two together. I wish I knew a quicker way of doing this, but this is where we're at. Oh, before I move on from the limacon, let's look at its properties. So we are here at the limacon. My domain is all real numbers, everything goes. My range, and this is something that I'm going to encourage you to play with more. It goes from A minus B to A plus B. So you can kind of plug those in and see exactly how that works. It is a continuous function, or continuous graph at least. Its symmetry is interesting. It's based on whether it's cosine or sine. If it's cosine, it's going to be symmetric about the x-axis, just like it was when it was odd n in the rose graph. And then if it's sine, it's going to be symmetric around the y-axis. All right, this one is bounded because, as we saw, it stayed within its little circle. Its max r value is whatever a plus b is. Again, explore that. And then there are no asymptotes. All right, let's go down to the spiral. This one's kind of cool. So the spiral is just r equals n theta. If you see, there's in here, there's no sine or cosine. So that's kind of how I know it's going to be a spiral. And it's called a spiral because it makes a spiral. There's really no other property that we're going to explore more. Makes a spiral. Before we look at the graph, we're going to go do the properties of this and the lemnis skate, just so we don't have to keep switching back and forth. When we look at this, we'll see that the domain is all real numbers and that the range is also all real numbers. This is continuous because, as you will see, it will keep going and going without you picking up your pencil or without the calculator having to stop and restart. It has a symmetry about the y-axis always. So no matter what graph it is, it will always be around the y-axis. And this is our first unbounded graph. And you will see momentarily what I mean by that. Since it's unbounded, there's no max. It keeps going out and out and out and out, and there is no asymptote. Okay, let's do the lemniscate while we're here. This one is special because it's the only one that has an R squared. So I've kind of pointed out specific ways of looking at the formula or looking at the equation that's given to you and finding out exactly which one it is. And all of these have specific formulas. So from the beginning, you can see, like, based on this equation, it's R squared, so it's got to be a lemniscate. In order to graph it, if you notice when we go to the graphing calculator, it doesn't give you an option of R squared equals blah, 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 right? So in order to figure that out, we have to do R equals, and we have to take the square root of the other side. So even though the equation doesn't say square root, we're going to have to use it. And then the other thing is we're going to need small theta steps in order to graph. But you'll see that in a little bit, what I mean by that. That's a special thing on our window. I just want to bring it up that we're going to have to look at it, and we haven't had to look at it before. So for this one, we are going to graph R squared equals 4 cos 2 theta. For the one above, I forgot to mention it. We're just going to graph a simple R equals theta and see what happens. All right. So before we go graph these, we're going to go look at what the properties are. Again, just so I don't have to come back to this page. So properties of the lemniscate. This one's not as defined as the other three. This one just has a special domain, and so we'll look at that in a second. It's dependent on the equation, and this is not that important to me that I want us to really focus on it. So it just depends on the equation. We're just going to leave it there. Our range, I didn't do a lot of exploring before this, so this is something you can do and tell me if I'm wrong. I'm pretty sure they're all in between -2 and +2 because of the 2 that's in front of the cosine and sine. Again, if you explore more, we'll revisit this idea. Your symmetry is all of them, all 3 symmetries, x-axis, y-axis, and the origin. It's continuous on its domain. So you'll see in a little bit that there would be times where we could pick up the pen or pencil, but we're just going to say based on the domain that we would give, it's continuous. It is also bounded, and you'll see momentarily what shape it makes. It has a max of 2 because its max R is 2 based on its range, and then it has no asymptote. Okay. So these are properties. Again, they're not something you have to memorize, but they're something I do think you should explore, and that's what your homework is kind of going to ask you to do. As we graph these, or as we did graph them, you could fill these graphs in on your own, just know how to do them, know how to plug it in, know kind of how to manipulate your calculator. So now we're going to look at these last 2 graphs, and then we're done for today. So I'm sharing to my calculator. And again, I had all of these plugged in, so if you didn't plug it in now. I'm going off of the 3rd graph, and I'm on to the 4th one, just R equals theta. I'm just going to graph it, see what happens. Ooh, look how it's making a spiral shape. Let's see if we can zoom out a little bit more. Let's go zoom standard, because I'm not there yet. Okay, cool. So this, right now, my window just goes from 0 to 2 pi or 0 to 360. If I go in there and make a bigger theta, and I could even make a bigger y and x value and keep zooming farther out, and it keeps spiraling forever and forever. So it just stopped because it's only going to 2 pi. But if I made this go to more than this theta is in radians. So let's say if I made it 100 radians, I don't know what that's going to be. And let's make our x min and x max -200. Again, I'm not really sure what this is going to look like, but it should just be a much bigger spiral. That's my hope. -200, +200. All right, let's graph it, see what's up. Whoa. Whoa, that's wild. Okay, I don't know if you can see it, but it's super spiraled. I probably went out a little too far to see it all, but yeah, so it spirals forever and forever as far as you say it's for the window to go. So that's pretty cool. And then the last one we're looking at is the lemniscate. So I'm turning off this one. Again, play around with it at your will and at your leisure. When I go to my window, I'm going to make my max go back to my 2 pi. So I'm going to physically write in 2 pi, and that should make that 6 point whatever number. I'm going to keep my my theta step pretty small, and I'm going to go back to, I think, negative 5, positive 5, negative 5, positive 5. And we'll see if we need to change from here. So we don't know what this looks like. Remember, we got a square root in it. I told you we have to have a small step, and maybe my step wasn't small enough because I've got some gaps in here on my picture. So I'm going to go even smaller. I'm going to go 0.001. I'm sure on your handheld calculator it's going to go kind of slow. It's going a little slow on this calculator that's usually very fast for me. So if you're not getting results right away, just let it be. It'll eventually get there. And it makes an infinity sign. How fun. All right, so these are the 4 different types of polar graphs and some properties about them. Look back at this, feel free to pause, play with your calculator. This should just be kind of fun and explorative. Yeah, so this is a new type of video. I'm sorry for any technical difficulties, but I'm getting it up ASAP and I'm getting it to you as soon as possible. So thank you for your patience as I switch back and forth. And as always, let me know if you need anything. Okay, I'm gonna end recording now if I can.